Ma'am, can you hear my voice?
Yes, sir. Yes, sir.
Okay.
It's fine.
Good evening, participants. Today we can see some basics on semiconductor electronics, its materials and devices. Before going through, we know now what is the importance of semiconductors in today's world. Okay, without semiconductors, we don't have our mobile phones, laptops, and any other advanced medical equipments. Okay, even defense, right? Whatever the gadgets you look into, without now, like our colloquially, we can say without any chip, we cannot process it. Okay, so semiconductor plays a huge role in transforming our modern life today. Earlier, it was started with the vacuum tubes to control the flow of electrons. Then slowly, germanium came into picture. Then silicon replaced from 1960s. Okay, in 1960s, it blew up the market with this low cost preparation. Okay, and the easy process in manufacturing. Right, from up to now, it's dominating more than 60 to 80% of semiconductor industry. So one of the property in material that divides a broad category, if you choose on different properties of the material, one is the electrical conductivity. If you range the electrical conductivity and divide the materials based on the values, okay, you can divide them into three categories. One is conductor, semiconductor, and insulator. So in the range of conductivity, if you see this, the unit is Simon per meter. If the conductivity is greater than 10 power 2, okay, then it's known to be a good conducting material. Okay, most of the metals, alloys, whatever now we used in our home hold applications like copper wire, right, and the transmission lines. Earlier it was aluminum, and now aluminum alloy in the high transmission lines. Okay, so these are very high conducting materials that ranges from 10 power 2 to 10 power 8, and above that the special class we now classify them as a superconductors. Then in the comes to semiconductor, the conductivity values range from 10 power 3 to 10 power minus 6 or minus 7. We can't draw a perfect line in classifying them. Let me explain one by one. You can able to understand too. Because if you see here, in the case of the 10 power 2, the conductivity of some semiconductors are ranging in 10 power 3. Due to doping, what we are going to see, and a few of them already know about what is meant by doping. If you dope heavily, semiconductor can act like a metal too. We call them as a degenerate semiconductors. And whenever you have the conductivity or less, for example, 10 power minus 6 or less than that, there too we can find a few semiconductors. Namely, now whatever the semiconductors what we are using in for high power applications, gallium nitride, silicon carbide. Okay, those are having very low conductivity when you compare the normal one in case of silicon or germanium. Silicon sets the trademark in semiconductors, or you can say this is a bench where we treat as a reference as a silicon and we compare with others. And we can, when we look into insulator, the conductivity is less than 10 power minus 3 and ranges 10 power minus 18 and beyond. Okay, most of the insulators has glasses, polymers, okay, some ceramics materials. Okay, we all know in the wire, in the whatever domestic purposes, when you use a wire, the copper wire, that is the insulated material with the polymer. Okay, so these are insulators which protect us. So for applications, we need all any electric applications. We need conductor, semiconductor, and insulator. They combine together for our day-to-day applications. Okay. Next, let's move on to how we classify the materials based on the band gap. Before moving into the band gap, I believe you know about band theory, how the band arises. Just a few light on this. Let me take introduction of hydrogen atom. if you have a hydrogen atom, there is a single electron in it. So for example, this is the valence electron. Let me have two hydrogen atom. For our understanding, let me draw a scale, and here let me put one hydrogen atom at a distance, say at the origin, and let me move the next hydrogen to a far away from the this hydrogen. It told it's shown like infinity. I do know what is mean by practical infinity. That means there is no interaction between this hydrogen atom. Say if it is one and this is two, there won't be any interaction between them. Okay. If you move far away from it, then if you see, look at the energy level, it has one electron, that is 1s electron. Don't worry about this. This is a quantum mechanical representation of this 1s electron, which normally we use a wave function psi, right? Don't worry about this. And this is electron 1s energy level. Okay. So now, if I move this hydrogen from the infinity to a distance nearby, which is where the normally it forms a molecule. Okay, so let me draw for your understanding. Let me take a hydrogen 1. This is a positive nucleus with one electron here. Okay, and let there be another hydrogen. Two. Okay, when they are comes close to each other, this pure assumption. All right. So what happens? They starts to form a relationship. We know we call them as a bonding, right? We name it when they share, it is forms a covalent bonding, so and so. Okay, to attain the stability, right? So if you view in terms of charges, right? So normally this for a parent, if there is only one hydrogen is there, always we know that in the nucleus there will be a positive charge and the electron holds the negative charge. So there will be a Coulombic attraction between this nucleus and the electron will be there in the same atom. Similarly, this holds for the next atom too. So when they are come near to each other, what happens is this electron and this electron will give a repulsion or repulsive force, experience a repulsive force between them as their charges are same. And this nucleus and the nucleus will feel a repulsive force. But in turn, this nucleus will start to attract the neighbor electron. Similarly, this will also try to attract this electron. Okay. So this we used to call as a interaction in general. Okay. So this Coulombic interaction will lead to different phenomena in the energies. So if you see here, only one energy level, when they come close to each other, the energy level starts to separate. We know there are two electrons. The two electrons will have the same energy level when they are apart, like an isolated atom. Okay. So for 1s electron, obviously they have to have the same energy. Okay. But when you come near to each other, this interaction will split the energy level into two, or we used to call the system as perturbed. Perturbed means disturbed. Okay, disturbed due to this electrostatic interaction between them, right? So these electrons will be staying in a lower energy level at first, or occupy the lower energy level, and then if it is filled, then it will move on to the next energy level. Okay, this thing will happen, right, in terms of energies. Now let us expand our thoughts to not to 2 electron. Let me move to 3 electron system, or let me take 3 atoms first. This is practically not possible. Let us assume 3 hydrogen atoms, right? If they are come nearby, what happens? Okay, we know hydrogen molecule only exists. So if it is there, then if there will be a 3 energy level will be created, and these electrons will be occupying the first, as per Pauli's exclusion principle. Only 2 electrons are allowed in a system with the opposite spins, right? With a given state. So here 2 electrons will occupy the low energy level. Then the next electron will start to fill the higher energy level. And further it will become empty, the next energy level. Okay. Next, if you extend to 3 electron system like lithium, okay. Say lithium, there are 1s electrons in an isolated atom. It has a single energy state, even if you have 3 electrons or more number of electrons, right? The same for 2s energy level also. Okay, in the 2p, it is completely empty. It is now unoccupied. Now let us take a n lithium atoms, okay, and starts to bring them nearby. So let's say they are at a distance a, and this a marks the the bond length. You can take it like a bond length. Are we in terms of crystal structure, we used to define this as lattice parameter. Okay, the proper way is the lattice parameter or lattice constant. Okay, this bond length sometimes you can say it like a true, but in not all the cases. Okay, for your understanding, you can take that the distance between the two atoms at equilibrium, okay, where the energy is minimum. So when you have a one atom here and other atom here and followed by another atom with the same distance, okay, in a lattice, when they are arranged in terms of a solid, then you can see here a single energy level. Now where there can be n electron will have the same energy level when they are apart at a huge distance between them. When they come closer, their energy level starts to disperse, okay, and slowly you can watch there some of the energies level are said to be occupied and some are seems to be in means empty or not occupied. Okay, so we can understand this. Yeah, energy level, because of interaction between the atoms between them, they starts to disperse. So now what we have knows the same energy level E2 is, but it is spread between, say for example, EB to ET, right? The energy level for some energy levels. Okay, this we used to call this as a band. Okay, to here this is referred as the S band. Okay, 2s band. Okay, so now the same thing if we plot it in different way, right? In the solid, when the atoms are nearby, you can see there the energy levels forms a band, and then the energy levels are band forms a band here. These are valence band and these are conduction band, which are empty, right? And it moves on to a state, it goes on, we can name it up to a energy level where we used to call a vacuum level. This is true in a given material. Say for example, for considering, let me take a lithium metal itself. If I supply energy, the electron starts to free itself, right? Already the lithium is a metal, so it is a free electron, so it's freely to move in the lattice, that means within the metal lattice. If the kinetic energy starts to increase, slowly it will moves in a way that it will move out of the metal itself. Okay, so when we say out of the metal, it can't come back, the same electron can come back, right? So we call that energy as an infinity level or vacuum level. So when you move an electron from where you can able to see to the level where you can make it out of the metal, we normally some work done is done in the process, we call that as a work function. Okay, so this forms a reference when you draw a band energy diagram for any materials. Okay, so this level is more important when you draw a band energy, right? Let us name that energy as 0. From there you can start a plot towards the negative axis. Say here the schematically is shown for your understanding. Say this oneness electron which is near to the nucleus is called core level. Okay, then that forms a 2s band, right? Which you can see here, it's also overlap. Okay, so there is a overlap between 2s and 2p, right? These are mixed. Similarly, there is a mix between 2p and 3s, these are empty. Okay, right? Since it is a metal, we all know there will be no band gap presence in this. Let's see that. And this is the shown in your textbook, right? This is the band energy level of a silicon. So silicon or germanium will have a valence electrons of 4. So you all know what is the electrons is 2s2 and 2p2 for silicon in terms of isolated atom. Okay, and in the case of germanium, it is, you can understand, right? It's the same s2 and p2, right? So if you see here, when they are isolated, right? So if you take 2 atoms, then there are 8. Okay, So there will be in the 1s2 there will be 2 electrons, and 2 pieces there has to be 6 electrons. Whether it is occupied or not, there will be energy levels. So there are 6 energy levels will be there. The same, this is given in the book as 6 n states. N stands for the number of atoms. Okay. Say if you go for when they are come closer from the infinity, that is from the region A, they are isolated. That is, there is no interaction. In the region B, there is a slight interaction. The energy level starts to disperse, and region C, the interaction is more. And when they come to their normal at the equilibrium distance, right, in the lattice, you can see the dispersion. So the same, yes, right, the energy level changes. It will decrease from, if you compare this original energy level to when they are isolated to when they are forms a solid, right, when the atoms comes nearby and forms a bonding between them and makes a solid, right. So when they are there, you can see the dispersion is more. That means the energy level changes, that it decreases as well as increases. Okay, right. So you can observe a energy gap formed between them also. Clear? So in between the band, there is a energy gap. We used to call this the forbidden gap or band gap. Right. This is like based on band structure, we can classify the metals, semiconductors, and insulators by their band gap values. If you see the metal, like we explored in terms of lithium just before, you can see the valence band and conduction band overlap. Okay. That means the electron, the same electron, valence electron, is free to move in the lattice. So the same, it is same as the conduction electron, since it forms a metallic bond. Okay. So obviously, if you draw, the energy level will overlap. Okay, there won't be any band gap. Whereas in the case of semiconductor, like we noticed, when they form a bonding, right, there won't be any free electron in an ideal case. Okay, this forms a band gap between them, between the valence band and conduction band, right? And you can see here the band gap can ranges from 0.1 to 4 electron volt up. Normally, the previous reference is 3 electron volt. Now we are being used to called wide band gap semiconductors. Okay, like what we are using for LEDs, lasers. Okay, these materials are having high band gap energy. Say if you want to shine a blue light, right, or ultraviolet light. Okay, you are using a semiconductor whose energy is greater than 3 eV. Okay, the UV range starts from 3 eV. So the semiconductor range slightly shifts from 0.1 to 4 eV now, right? These are like a reference value. It's a relative one. And in the case of insulator, the band gap is too high. It's greater than 4 electron volt, and normally it's difficult to move the electron from the valence band to conduction band with a low energy, okay, or with the practical purposes. Okay, right. So we can classify based on the conductivity as well as the based on the energy diagram, metal, semiconductor, and insulators. And we all know the holes will be in the valence band, and the electron which were free, which is moving, will be in the conduction band. This for your reference, there are different materials can form, right? Say for example, here I started with a diamond, yeah, insulator whose band gap is 5.47 eV, and you can see the reference silicon is 1.12 eV is at room temperature. Okay, at low temperature is 1.18 electron volt. And germanium, you have 0.6s, and you can say tin semi metal. You can have bismuth, some tin, where you can have very low band gap. Okay, bismuth normally there won't be overlap, but there will be slight touching of valence band and conduction band. Okay, so that category we will call them as a semi metal. If you see gallium arsenide, the band gap is 1.4 to eV. Gallium nitride 3.4, indium phosphide 1.36, and goes on. This list is like 26 zinc oxide, this is 3.3, right? And you can move on. Okay. So basically, we have the conductivities. Normally, when you study a textbook, we say intermediate between metals and insulators, but As a student, you have to remember the value. Okay, when you are asked a question, you should not say it is the conductivity is inter between metals and insulators. I have to tell this range. Okay, it will be between 10 power 3 to 10 power minus 8. Okay, now let's move on a little bit. Classification of semiconductors. The different way one can classify the semiconductors based on their property, based on how they are formed, right? And how it is being used also. Okay. One fair straight away classification is elemental and compound semiconductors. In the elemental semiconductor, you can have only one element in the whole solid. In the compound, it is a combination of one or more elements, sorry, two or more elements, right? Combined to form a semiconductors. All right, let's see some example. In the elemental, we know the silicon, germanium are called elemental semiconductors since only silicon is there and germanium is there, only one element. Whereas in the compound, there are different ways. There are many possible combinations are there. Let's say technologically important and what we are using now in day-to-day life, right? We can see those group. This is a old periodic table. Don't take this as such. These are based on their valences. Okay, group 3 and 5 miss group 3 valence, miss 3 valency and 5th valency atoms join together to form a compound. Gallium arsenide, gallium nitride, gallium phosphide, and their alloys. You can take like indium gallium nitride, aluminum gallium nitride, and so on. And in the case of other classification, in the case of zinc, in the group 2, yeah, I don't know the correct group now. This is the old one, group 2 and group 6. Okay, these are based on the valences, right? So zinc oxide, group 2, there is 2 valency, and oxygen is 6 valency system. Okay, and zinc sulfide, zinc telluride, and so on. Cadmium sulfide, magnesium oxide, move on. And group 4, that is 4 electrons, like you can form silicon carbide, silicon germanium combined together to form a compound semiconductor. And many other possibilities are there. Now you can have, these are whatever I named here is mostly on inorganic case, and you can have organic semiconductors too. Okay, now you can see the TVs are organic LEDs, right? TVs are powered. Now we have, so these are organic semiconductors, right? So many more combinations are possible. All right, let us move on to based on their carrier and how they are being prepared. Okay, then the semiconductor can be classified into intrinsic and extrinsic semiconductors and how they are prepared. If they are in the pure form, that is no additional impurity are added to it intentionally. Okay, mark my word, it is intentionally, it is not added. During the experimental process, we can't have a perfect. Okay, so there may be impurities present, which is unavoidable in any process. Okay, so we call them as an intrinsic case, right? If we are not purposely added any elements to the host semiconductor. Say silicon is simply silicon, germanium is simple germanium lattice. And then if you add some other material or foreign element to a host, okay, in terms of very small percentages, normally we used to call them as parts per million, right? The way normally we used to say the number of atoms per million host atom is called parts per million, right? Or you can say in terms of atomic percentage. If you know, you can calculate and you can add it during the growth itself or after the growth too. Okay, these are added to change the character of the host to something what we want. Say for example, I need a polarity change. Say I need a more hole rich, that means positive polarity. And in the case of some semiconductor, I can dope it in such a way I can bring it right with less electrons. We see one by one, right? These are termed as extrinsic semiconductors when you add foreign elements intentionally to the parent host. Okay, then how you define an intrinsic semiconductor? to be frank, in an ideal case, you have to consider a perfect crystal with no impurities or crystal defects. Okay, they do contain electrons as well as holes. I'll just start what is meant by holes. Please take the word like if you define the intrinsic semiconductor, then at any instant of time, the number of electrons in the conduction band will be equal to number of holes in the valence band. If it is matching, then we can call that semiconductor as an intrinsic semiconductor. Then you can ask me, sir, you told in practical case you cannot avoid impurities or defects. Then how can be it can be intrinsic? Okay, so in those cases we will watch the carrier concentration. Okay, normally in the case of silicon, you can see the range is 10 power 10 per centimeter cube, right? The carrier, that is whether this we used to call intrinsic carrier. This contains both electron and hole, and it is in this order. It is very low actually. For our practical application we need more, right? Here the resistivity is too high, right? So we will dope to get more carrier concentration in terms of their polarity. Okay, a p or n type, right? So whenever in its purest form and it grows, it ranges from 10 power 6 in compound semiconductors to elemental semiconductors. When they carry concentration, it is 10 power 10 per centimeter cube. Then we term them as a practical case as intrinsic semiconductors. So keep the word correctly. Practically, we have carriers. Okay, even though they are not ideal case, their conductivity is low. Okay, right. Now let's investigate on silicon. Silicon has a um, system like of 14 electrons. Okay, so in the previous band diagram I told about 2s2 2p2. Correct me there. It is 3s2 14 electrons. So we have 1s2 2s2 2p6 forming a 10 electrons as a core energy levels, and this is core. We used to call this a semi-core energy level, and this is the valence, right? So valence electrons are 3s2 and 3p2. You all know what is mean valence, the outer orbit of an atom. Okay, so in an isolated silicon, you have 3s2 and 3p2 as a valence electrons. So what's so special in this? So what happens is, if you see here, when you bring two silicon close, okay, like I told before, say one silicon atom is here, and when you bring another silicon atom nearby, right? And we all know, right, there is a covalent bonding will be taking place in between them. So due to the interaction between them, right, like we discussed before, the energy levels get modified in this silicon electrons. Okay, so what happens is this 3s2 and 3p2, their energy levels will have the same values, or they started to mix together. We call that in terms of another word called hybridization. Okay, mixing of energy levels, right, in the same atom, we used to call them as a hybridization. So 3s, this is s electron and p electron will energy levels will mix together. So since they are having same, and when you come to stability, the atom prefer 3s3, sorry, 3s1 and 3p3 rather 3s2 3p2. Okay, so we call this as xp3 hybridization taking place in a single isolated or not isolated when you two silicon atoms comes nearby. In the isolated case, it is still 3s2 3p2. Okay, so this they forms 4 valence electron, which is shown here. The cores and other things are excluded in the schematic diagram. Okay, so when you see here, right, the valence electrons are dispersed like this and they are around the atom. This is schematic diagram. Don't worry about what is the what is the actual case, how the electrons and revolt, still more research is going on. Okay, what we are thinking like an electron as a particle, still there are theories that they are not taking directly as a particle. Okay, so let's say a charge revolves around the nucleus, right? 4 charges are there. So when you two silicons comes nearby, we know to attain the stability, that is to get a closed orbital, they will start to share the electrons. Okay, so a silicon in this case, if you see here, right, they will have a electron shared with the neighbor, right, across all the directions, right? So if they start to share the charge density, right, or in terms of quantum, we just used to say called overlap of wave functions. Okay, when they start to do that, then we say that the bonding starts to be established. Okay, so if you see here, by each cases surrounding them, right, there are 4 electrons will get shared from 4 different silicon atoms around them. Say from here, you can see this will have one atom, one electron, this will have one electron, and this will have one electron here, and this will have one electron here. So this gets 4 electrons to be get filled. Okay, so then it can have, like it's assumes to have kind of a configuration like this, but it's not going to be this, like a sharing, right? So this attains stability, so the no more free electrons are available in the lattice. When we draw an energy level for this valence electron, we call them as a case which is called valence band. Okay, and here, when the electrons are not free here, if it is supposed to be free, the energy levels, they are composed, right? We call them as a conduction band. Okay, like we noticed before in the band theory, there is a band gap between them, between the valence band and conduction band. Okay, this is a schematic simplified view for your understanding. Okay, 2-dimensional view. Right. Now, okay, here you can notice something is I have written here. You can see during the band diagram for our representation, the band gap is normally written as E suffix G. Okay, and the top of the valence band is written as E suffix V. That is the topmost energy level in the valence band. This marks as E suffix V. Okay. Similarly, the bottom of the conduction band, we used to call conduction band edge. Okay, it's called E suffix C, right? And like we told before, the vacuum level where the electrons can move away from the semiconductor itself, right? That energy level we used to call as a vacuum level. And here, in the case of metal, normally we will write with the work function. Here we are writing with the electron affinity. This is from the electron affinity from the bottom of the conduction band to top. Metal is slightly different, where you used to call a Fermi level. From the Fermi level to the top of the conduction band. That's a vacuum. Okay, right. So this is forms the intrinsic silicon band structure. Okay, right. Now we used to do word now. I believe you all know what is mean by holes. Okay, holes are electrons. We know this is a particle that is present in the lattice. In each atom, we knew that. We just spoken about the bonding, their energies, and so on. So what about the holes? Holes, suppose if you see the electrons are missing from a bond, okay, then what happens? There is an empty place in it. So absence of an electron is referred as a hole. And if you see here, in the presence of a bonding, if there is an electron in the bond, here there is no extra charge is present. Okay, once the electron left this bonding, then it leads the electron is a negative charge. So when it starts to move, we refer that the electron is a negative charge is moving in the lattice. So how you understand here that here it is neutral, but when he starts to broke the bond and move an electron away, then electron holds a negative charge. So just a simple logic, what we see is +1 - 1 is 0. Okay, +1 charge and -1 charge. When you sum it up is 0. That was here, right? So if an electron moves from here to somewhere in the lattice, negative, right? So now initially it is 0, right? So an electron 1 is moved, -1 is moved. So this place where the electron is not there, we have this charge +1. Okay, this is for our understanding we did, but practically it works. Okay, so we call this as a empty place as a whole in the lattice. Okay, all right. Then there are different way you can break the bond. You can heat it, you can shine your light. Okay, you can give mechanical disturbance also. Okay, the electron will starts to move in the lattice in the case of silicon or germanium. So let's have this diagram. Let me draw a line, two-dimensional pictorial view of silicon here. The covalent bonds are represented two lines surrounding the atom. Okay, these are valence electrons, right? Each line is a valence electron. Okay. Now, if I starts to heat it, for example, whatever here it is drawn, we say it's happens at 0 Kelvin. Okay, right? So at 0 Kelvin, and the temperature is 0, absolute 0, then we say that the atoms doesn't vibrate. Okay, it doesn't have energy from the surroundings. As a physicist, you all we all know in the physics, whenever you consume some energy, some work has to be done. Okay, so when there is an increase in temperature in the surroundings, normally even the room temperature, you all know the temperature energy that will give us kBT approximately. Okay, right. So this much energy will be consumed by the system. So when this is being taken out, T is the temperature, K B suffix, right? B is Boltzmann constant. This has to be, atoms has to do some work. They will start to vibrate. Okay, during the vibration, if the vibration is so enormous, right? These bonds are elastic. So if it is more than that, what happens is the bond broke, and then the electron free itself from the bonding. Like I described before, the absence of electron in between this, right? We call them as a hole. In terms of band picture, you can see this type of thermally excitation, right? Thermal vibrations we used to call thermal excitation. Why word excitation? It moves from the lower valence band to the electron is freeze, right? Since it's free, now if I give a power supply to this electron will start to move towards the positive side of the battery. Okay, so this electron now it's called as conduction electrons. Okay, it's free from this atom, right? It can move in the lattice. So here, this electron's energy can be drawn here, right? So in the conduction band, or conventionally, we say that the electron from the valence band will excite to the conduction band. Okay, the way of excitation here referred as thermal excitation. Normally, when the band gap is low, this you can expect this kind of thermal excitation in semiconductors. Okay, right. Let's move on. Then, what is the first thing? What is the difference between a metal and semiconductor? Metal, the free electrons are available in the lattice. So whenever you give a power supply or voltage, the electrons are ready to move towards the positive side of the battery. So what is different in semiconductor? In metal, it is a unipolar conduction, whereas in the case of semiconductor is a bipolar. So what is bipolar? Like we define electrons and holes, right? I'll write H, right? H plus, I think you understand now as per the discussion. Okay, so the electron holds a negative charge. This is one charge and the holes, right? Whenever there is a electron is displaced from the bonding, there a hole will be created. Okay, so there is always a bipolar conductivity will be there in a semiconductor. Next question. Sir, if I starts to give, let me take a semiconductor solid, right? Now I'm giving a negative power supply here and positive power supply here. Then we understand that electron since it is a negative, it will be moved towards the faster power supply. Similarly, absence of an electron, conversely, we have to say that it will move towards the negative side of the battery. Okay. Now, just now, sir, you have defined this as an absence of an electron. That means an empty particle. This is not a particle. Then how you can say and there is no particle, but how it moves towards the negative side of the battery? Okay, this is a normal doubt that comes in the students. You can see this pictorially here. Whenever the electron starts, right, if there is a electron is ejected from the bonding, right, a bond is broken, what happens is from the neighboring bond, right, in the same atom, I can say here there's another atom from the which is within the distance, right, where there is an overlap of energy level is possible, right, this electron from here will migrate and to the bond to and forms a bond here. Okay, so a hole which is here, right, will be occupied by an electron here. Okay, so this hole will in this and it will establish a bonding and hole will be created in the neighboring site. Okay, this process is actually electron is moving, not the hole. Okay, so see from here, I can say here from this neighboring bond, the electron starts to see a vacancy site nearby where it can move. So it starts to move here. Actually, in terms of energy, we use state it tunnels through with the bonding in between the energy states, right? And this mechanism we used to call hopping mechanism. Okay, so still I can't understand this. Let me give an example. Let me take a water bottle, right? Let me have a water bottle. Okay, now let me fill miss up to some stage with water. Okay, now here is the air gap or bubble. Here these are waters. Water molecules are present in the vessel. Okay, now if I tilt this water bottle like this, let me have my drawing is poor, please adjust with this. Okay, then what happens, the water you can see here, the bubble starts to come in the top level, and we will see the bubble present in one state. When we tilt it, the water bottle, the drop miss air bubble starts to move upward. But what actually happens is the air bubble, because of density, it's moving, but the water is displacing from its position and filling up depends on the lower to higher state. That means how the slope is. Okay, in the water bottle. So the movement of the water, it gives our eye the bubble is moving from one place to another. Okay, the same analogy you can take it here. The movement of electron from one bond to other will give a feeling like the hole is moving from one place to another. Okay, and this mechanism we used to call hopping mechanism, the migration of electron from one bond to another. All right, so if the electron is free, is it as it is? No. What happens is whenever there is an electrons being created and it is moving around the lattice, when it comes near to the vacant site in the nearby the bond, then this electron starts to fill the bond. You can see here. Okay, this electron starts to fill the vacant place in the bond and re-establish the bonding. Okay, like how we are saying here, it is migrating from the one bond to another. Here slightly different. This movement, this electron is free. Now it is moving very freely within the lattice. That means it doesn't have that much influence from the atoms. Okay, so the kinetic energy is more now. So when it comes to hereby, it has to lose this kinetic energy. That means we here when it comes and be formed here, its movement is arrested, and we used to call that as a delocalized. You all know, sorry, when it is moved, we used to call delocalized. When it comes and localizes its position, okay, nearby the atom, right? Then the kinetic energy has to be zero. Okay, then this as I told, energy it conserved, right? So it has to be given out. So if in terms of band perspective, you can see there the electrons in the conduction band here will just come and recombine with the hole here. And this, I told recombine, this process is called recombination process. Okay. The difference in the energy will be released in terms of heat or light. Okay. Right. Now let me move on to extrinsic semiconductor. Let me take a silicon as an example, right? When I add impurities to the silicon and make this like one polarity much greater than the other. Say, for example, I need a positive polarity, right? Excess of holes to be present in the silicon. So this type is called P type. How it is achieved? Then if there has to be excess of hole, then I have to reduce the valence electron. So how can I can do that during the growth or after the growth? I can modify the process such a way that I have to replace the silicon with some other material which has one valence electron or one or more, okay, one or more than the silicon, okay, right? So if I do that, then I can able to achieve the P type. Similarly, if I need a negative rich semiconductor, that means extra electrons to be present in the semiconductor, then I have to dope with this process of adding, right? It's called doping process. Okay. I have to dope with an extra electron atom to the silicon. Okay. It can be, right? It can be one electron or more than one electron. So say, for example, silicon valence is 4. So I have to add 5 or 6 valence, right? To here. Okay. Normally this is preferred. Okay. Then this termed as an N type. So now if you see here, it say I took an example for N type. I don't know whether it is visible or not, the heading to you, right? So if you see here, let me dope with a arsenic or phosphorus, which has a 5 valence. Okay. If I dope after the bonding, there will be extra electron will be there in the atom. Okay. This extra electron will act like a negative charge to the system. Okay, how much number of this x miss plus 5 valency, sorry, 5 electron system you dope within this silicon will give us number of electrons, excess electrons in the system. So if you take an arsenic, right, this arsenic have 5 electrons, the 5th electron, the 4 electrons in the arsenic will bond with the neighboring silicon. The 5th electron will revolve around the arsenic. It doesn't desert as such, right? It will move around the arsenic. That means it is still localized. It is not delocalized. That means it can't move away from the arsenic unless until you give some energy. Okay. So in terms of band structure, okay, we used to call this atom whichever donate one electron to this silicon, right? This is a donor atom. Okay. So the number of donors, right, will give an idea about how many carrier concentration will be. Say if I add 10 power 12 arsenic, okay, this will be equal to the number of electrons. If I say n is the number of free electrons in the conduction band, almost I can say this will be the maximum number it can have at lower energies. Okay. So if I draw an energy structure, this is the valence band. Okay, let me concentrate on the near to the conduction band. Since this electron is a non-bonding, right? Non-bonding electron, it has more energy. Okay, so other 4 electron of arsenic will be there in the valence band. The 5th electron energy is high and it will be near to the conduction band. Okay, so when you give slight energy, this electron whichever present in the arsenic, right, it will move away from the arsenic. That means you are ionizing the arsenic, and the arsenic initially it is arsenic 0, the charge is 0. When you give some energy, it will become arsenic plus. Okay, so here the energy separation, right, between this and this level, since it is for the donors, we used to call this as a donor energy level, right? So this electron from here will move to the conduction band when you give the energy equal to this 50 milli electron volt or 0.05 electron volt. Clear? It is easily conductible in terms of our room temperature. Okay. The same thing you can go for p type too. In the p type, I have to add an extra atom which is less than valence of silicon. Okay, so in case I will take boron. Okay, boron has 3 valency, so it when you add it, it can't bond. One bond is left behind in the within the neighbor of the silicon. Okay, so if you calculate the energy, this extra electron right here presence will have an energy there. In the band structure, it will form just above the top of the valence band, and this atom which ready to accept an electron here to form the bonding, right? This atom is called acceptor. Okay, whichever we dope in the silicon with a less valency are called acceptors impurity, and this energy level is called acceptor energy level. Okay, so it readily accept an electron from the another nearby silicon to here. Okay, so whenever this electron comes from here to here, right, it is shown the energy diagram as such. Okay, it leaves a hole in the valence band. Okay, so like electrons moves in the conduction band, holes will move in the valence band. Okay, right. And so now these are this different dopants that is commonly used in the industrial process for silicon and germanium. You can watch here the germanium, the energy is little bit less for the same dopant. Okay, it depends on the system, right? So if you say case of phosphorus, like we approximated around 0.05, actually is 0.44 ev, and arsenic is 0.049, and antimony is 0.039 in the case of silicon n type. You can see in the case of germanium how much it is near to the conduction band. Okay, so this amount of energy, if you give this electron will be moved to the conduction band or free to move. Same goes for the p type also. You can take 3 valency atoms to the 4 valence silicon or germanium and make them as a p type, and these are the corresponding ionization energies shown to you. Right, and this is a comparison. Like I told, say for example in intrinsic, how you define the number of electrons in the conduction band will be equal to the number of holes in the valence band. This is the band structure diagram, and this Fermi level I have not discussed to you since it is not in a textbook. This Fermi level you can treat like a metal. I will just, for your understanding, you have a bucket of water. Okay, how you take a easy way of taking water from the bucket is the topmost filled water level. Okay, you just plug from the topmost level, or you can take it like this. The same way in the metal, if you start arranging the electrons based on the energies, the topmost energy level at 0 Kelvin, what remember at 0 Kelvin is the Fermi energy. Okay, but in the case of semiconductor, the Fermi is nothing but a distribution. Actually, it's a property distribution. It's not a correct. You can't say an electron will be here. Okay, in metal it is an electron will be there, whereas in the case of semiconductor, it's kind of a probability. It gives an idea where we can find the carriers. Okay, whether it is an electron or hole, where we can able to find the carrier, right? It's just keep in mind, it's just nothing but a probability. So in the case of n type, you can see there, like in the case of donor, probably near to the donor, you can find the Fermi level. It will be in between, in most cases, between the conduction band and the donor energy level. It depends on the concentration of doping as well as the temperature. This depends on a lot of parameters, the Fermi level. Okay. Similarly, in the p type, it will near to the valence band in most cases, and it can move to the valence band also. And like I told, this thing n equal to p, there is number of electrons and number of holes will be equal, and it is called intrinsic carrier concentration. Okay, there is a law called mass action law. This law holds good on all these cases where there is the equilibrium is maintained up. There is no external force has to be given. Okay, if it is not external means energy is given to the system, then we maintain that in equilibrium. Then let's say, right? So say n into p, right? We used to call this will be in the intrinsic case n square. Okay, this is called a mass action law. The product of electron and hole will be equal to the square of the intrinsic carrier concentration. Nothing but these both are equal. So we can write n square. This we can use to find in the n type there is a hole, right? So based on the mass action law, you can use also the hole. Here it is called minority carrier, and electron in the n type is a majority carrier. Okay, so the hole in the valence band you can compute using the mass action law, right? And like I told, the extrinsic, that is in the extrinsic case, the dopant will be equal to the carrier, that is whether it is n type or p type. Okay, so you can use that there to calculate the mass action. By based on mass action law, you can be able to calculate the minority carrier in respective systems, whether it is n type or p type. Okay, to moving to the device. Okay, what happens, why we semiconductors are more important, right? These are applied like in our electronic devices. We start with the basic diode. To move into diode, we have to understand some concept before that. If I ask you in the nature, let me take a room. I'm just opening a perfume bottle at the one end of the room. What happens? These aromatic compounds are present in the perfume, right? So once it comes out at the other end, if you are present in the other end, you can be able to smell it. How it happens? It moves from one end of the room to the other end. How it does? The aromatic compounds are denser at one part of the room, and slowly it moves, that is, it diffuse from one part of the room where there is a higher concentration of aromatic compound to there is no, the other end of the room there is no aromatic compound, right? So it slowly diffuses in the gases and comes to the other end in the space, let me tell. All right, so this happens naturally. The diffusion, we call this as a diffusion process. The same way the electron or hole will also diffuse, right? Here, for your understanding, let's say a hole is injected by some process by doping, right? So if you take a semiconductor normally, if you take a wafer, there is a process called ion implantation process. Initially, the silicon dioxide, for your understanding, is spewed and taken as a silicon polycrystal and put it in a crucible, and in a furnace, it will melt down, right? And slowly it will be melted and liquid will be slowly cooled and pulled up. Okay, it forms a huge crystal. Okay, and it will be bigger than our size. So even now, 6 meters, they are growing with a 12-inch diameter. Okay, and it will be sliced into small thin wafers. This thickness around 300 micron. Okay, from that base they are forming the uh, chips. Okay, so when you take such kind of a wafer and if you want to dope it, you can simply you keep it in a other process where you can inject some, say for example, I want to inject hole, I will pass the boron atom with the energetical boron atom to come and hit the wafer, and it, when I heat it, it starts to diffuse. Okay, that way I can dope it. We call that as an implantation process. So in the way it doped, say here at one end of the semiconductor, it is hole rich, and when you move on, it is slightly low. Okay, so the whole concentration, if I draw a graph for this, I'll say, let me take this an x-axis. At 0 at the end, it is more holes, and when it moves on, the holes concentration decreases. Okay, similarly, if I dope in the case of electron, then also you can see here the electron rich at one end of the semiconductor, and slowly I move on, the electron is less. So what happens here, like the nature, what you do, the hole starts to move from the higher concentration towards the lower concentration. And when, since these charges are moving from lower to higher, when you move charges move, then we used to call this a current. Okay, this current is called diffusion current. Okay, this is a natural tendency for all carrier to move from higher concentration to a lower concentration regions. Okay, another mechanism, when you start to supply a power supply in a, like in the case of wire metal or in a semiconductor, the electron will starts to move towards the positive supply. Okay, this is a pulled like a attractive force, right? So here it is, we used to call this a drifted towards the polarity of the power supply. Okay, or some force is applied to move the carrier. Okay, so such movement of the carriers are called drifted due to the field presence, electric field presence. So such current we used to refer as a drift current. Okay, now let me join to PN. So how it is possible? Take a wafer. Like I told you, grow a P type and you can put an N type implantation. Now you have a interface of PN. So let me show an animation here. Here this is a P region and here there is a N region. Then they are combined. They form an interface. This is we used to call PN junction formation. Okay, like you can ask me, this is our electron. Like I told, there is nothing is perfect. Okay, so there will be a minority carrier, like due to defect, there will be always few electrons in the P side and few holes in the N side also. Okay, so how it forms? When it starts, the diffusion starts. Now what happens in the N region? N region is rich of electron. So what happens here? It is less electron. So the electron from here starts to move towards the P region. Okay. Similarly, the hole get occupied. That means the electron starts to occupy, fill from here. It will start to fill. So slowly the hole get migrated towards the N side. Okay. So we can see there, once they are moved, then like we discussed before, say for example, a boron in an cell, it receives an electron. Okay, with the bonding of silicon. So initially the boron is 0 when the valency is 3. When it receives an electron in an orbit, then it becomes a negative ion. This negative ion is showed in the P type region, like minus. The blue colored region is the doped boron. Similarly, we have phosphorus, which is a 5 electron, right, or arsenic. When it leaves an electron, when it leaves from it, then it becomes 4. Okay, then it becomes P plus, or arsenic, if I say arsenic plus, it becomes a positive ion. So these are shown here in the blue circle. So this will be in the interface. They will be in the interface, these ions, right? So when these processes are happening, we just say from the N type here, the electron starts to diffuse towards the P type, and the similar manner, the hole from the P type starts to diffuse towards the N type. Okay, and slowly what happens? There will be a region in the interface which is depleted, because there will be recombination will be there when both are joints, right? I shown in the animation. So this is depleted of any free charges. So it named as depletion region. Okay, depletion region means depleted of free charges. Okay, but what happens there? There will be like we mentioned before, there will be a boron plus in the boron minus will be there in the P type, and phosphorus plus will be in the N type. Okay, these are ions, they are immobile. Okay, so this, they will have, these are charges, right? So we all know from the basic of electrostatics, whenever there is a charge, there will be electric field around it. Okay, so this creates a field, right? And due to this field, this whatever the electron starts to move from here, this will be opposed by this phosphorus negative ion in the lattice. Okay, so initially the diffusions will dominate, and once the diffusions in the interface going some time, right? Once this charges, immobile charges develop more, then they will start to drift this electron. Okay, that means whichever comes here, they will repel and it will move away. Okay, so the electron will be drifted back, right, towards the end. The same thing, it happens in the P type also. The P type, there will be immobile, that is, sorry, this is a P type and this is the N type. Okay, immobile negative. And in the case of N type, there will be a phosphorus plus. So they will oppose the whole movement towards them. Okay, so the whole will be drifted away, right? When these two balances, Okay, when the diffusion process balances with the drifter, okay, then this junction will stabilize. I'll come to an equilibrium. Okay, so here, since they are depleted of charges, it's called depletion region, and this region, when these two process it comes to an equilibrium, they will cover a region in terms of 1 or 2 micron. Okay, depends on the concentration of the electrons. Okay, right. So this was shown in this here. So they will have a electric field between them, and they starts to develop a potential between this. We used to call a barrier potential. You can't measure with an external. You don't think like I will measure, since there is a potential, whether I can able to measure with multimeter. No, it will be internal potential that is developed. Okay, you cannot do it. Right. Then in terms of bands perspective, if we draw this, right, let us combine this n and p levels, right? So you see p region normally it will be higher in energy and n region will be lower. So whenever the electron starts to move from here to here, right? Say this diagram has to be based on the Fermi energy. I have not shown here, right? So you can see here, slowly the electrons moves. Then when the electrons moves from here, then the energy level of the N slowly decreases. Okay, whereas the P starts to increases, where the electrons increases. Okay, so in terms of bands perspective, what happens in the conduction band is they won't be uniform. Okay, there won't be any flat linear line between P and N energy levels, although they are same of silicon, right? The electrons, since it is moving from N to P, the energy level of N side will decreases and P side will increases. There will be a gradient will be there. It is shown in the animation. It is shown like this. Okay, right? This is the EC of say N type, N region. This is the conduction band minimum of P type. Okay, so this region is a higher energy. So now once the band is once the depletion region is equilibrium is established, then there will be a difference in their energy. So now the electron from here cannot freely move to here. Okay, since it needs an energy to move, there is a difference in energy between this conduction bands. Okay, so how to do it? How the diode works? If there is a difference in energy, then we have to do some external bias to it. If we join based on the polarity, the bias is differentiated into two. One is forward bias and another is the reverse bias. If you add P type power to the positive side, if you connect, right, then as well as N type to a negative side of the battery, then we used to call this a forward bias when the polarities are same. Then what happens? You can see as per the animation here, the electrons are pushed away, are drifted by the negative power supply here. So the N region, the electrons will be drifted, that is they will be moved or pushed towards the P region. So they will cross this barrier. That means the electron from here, the N side, this is the N side, okay, this is P side. The electron from here, they will get a sufficient energy and they will start to move towards the P side. Okay, right, and this is feasible. So once they start to move, and they will recombine with the charges present here also. Okay, this we used to call injection process. Okay, when it is being externally injected to the semiconductor in between them regions. Okay, now there are some terms you can understand. In P side, these electrons are minority carriers. So due to the power supply, what happens is we are injecting the minority carriers to the P type. Similarly, the holes will be there in the N region. There we are injecting the holes towards the N type. There is minority carriers in the N side. Okay, so this also comes to balance. Now, if I measure, right, if I connect an ammeter with this and measure the current up to some voltage, right, where the barrier slowly, here see 1, 2, 3, textbook is given. When you increase voltage slightly, say for example from voltage 1, voltage 2, voltage 3, what happens is slowly the electrons is pushed down. Okay, depending upon the energies given by means of voltage, this electron will be pushed. Okay, when the voltage is small, say it's 0 at this, the energy level may be much higher. Okay, so when it comes to one, say for example, at this, when I supply a 0.1 voltage, right, slightly the energy level decreases due to the energy supplied to this region. And when it is 2, say for example 0.5 volt, right, it will be like this. When it is 0.6, it will be around very small built-in potential, that is the energy difference is very small. Once you increase the voltage, right, up to where the barrier disappears, okay, literally you see the barrier, you cannot see it, will the electron starts to move freely from here to here, right, and the hole starts to move from here to this side easily. That voltage we used to call knee voltage or threshold voltage, right? So why we need semiconductor? This is, up to this you can see the process is very slow, and you can see above the knee voltage or threshold voltage, right, you can see the it is exponentially increases. Okay, it is the current is increases exponentially. This is the beauty of a diode. Okay, imagine I'm up to some voltage, I'm getting very small current. After that, I'm getting milliamps. Okay, so this is possible only in semiconductors. Okay, so suppose, sir, if I reverse bias it, what happens? If I reverse the polarity, that is, I connect the negative polarity of the battery to the p side and positive polarity to the n side. Okay, then what happens? The energy levels, right? The gradient starts still further. Okay, there will be the potential barrier will expand much further. Okay, and the depletion region widens. As the electrons are attracted towards the positive side, more electrons starts to move towards the positive side. Okay, and holes will start to move towards the n side, or the electron will start to come and fill the holes. Okay, so what happens, this region starts to have more and more means depleted of charges. Okay, so here there won't be in ideal case there should not be any current, the current should be zero. Okay, the flow of current should be zero, but like I explained before, there is no perfect. Okay, so what happens, there will be a defects, right? This defects will lead to holes in the n type. Okay, there will be small minority holes will be there. These are, I can say, minority carriers will be there in both n and p type. Okay, these minority carriers will start to move. Suppose if there is a negative, sorry, you can able to locate. Okay, so electron is here, right? This electron will be attracted and it will diffuse through the barrier and refuse. Okay, similarly, if there is a hole here, this will be moving here. This is pictorially I'm explaining, like you can understand, right? This is hole is not moving, actually the electron is migrating. So this, initially the voltage is very very small, the minority carriers will be very low, right? And this current will be in terms of pico to nanoamp, right, in a perfect diode formation. And when you further increasing, what happens, this start when they are moving, it's develops due to this potential, right? They develop a high kinetic energy. Okay, once a high kinetic is developed, they starts to disturb the lattice, they will starts to collide with the other electrons, not physical, like electrostatic force will be there with the other electrons present in the lattice. So this force they will use to displace more electrons. Okay, and then we that time we used to call there is a breakdown happens. This breakdown you can have two types, one is Zener and avalanche, right? You can see one electron hits another electron and free, and the two will hit four, and four will like a 2n, it will multiply, goes on. Okay, so this suddenly when they in terms of this voltage, this is in hundreds of volts. Okay, don't think it is 100, it is 800. It depends on the semiconductor, how much dope it is. So roughly I'm saying it is a 500 volt. Okay, don't take it as such, this is for your understanding. Okay, so this after this the voltage increase will give you a very high current. Okay, don't think that the diode gone bad. Okay, you can switch off now and you can reuse the diode as such. Okay, in each electronic equipment there is a called power limit. Okay, within the power limit, if you are able to use this diode, you can reuse the diode also, it won't gone bad. Okay, you can reuse it. When you exceed this power limit, then the due to excess power, it will damage the diode and you cannot do it. Okay, so this is shown the IV characteristics of a diode. Here when you cross the barrier potential, you can see there is an exponential increase in the forward bias. At the same time, the reverse bias, you have a after the knee that was very small knee, just the way of curve it is given as knee voltage, there is a breakdown voltage, you will have a enormous current flowing through. And silicon, it is in terms of hundreds of volts, and germanium also hundreds of volts. When you go for compound semiconductor, it is in terms of kilovolts. Okay, so you can understand for different applications we have to select different diodes. Okay, think if the time lets, I slightly quickly run through the application of a diode. Small, just a halfway rectifier. You have a AC signal. You can do by a transformer. You can step down the transformer, and then you can have, like, say, for example, I have 12 volt step down transformer. With that, I am just applying an AC signal to a diode, and to get the output, I am connecting a resistance to it. I call this the resistance the load resistance. Okay, so now let us see. We all know now, if it exceeds the threshold voltage, then if I give a voltage correspondingly, I get a current. Okay, in this case, I have to go up to breakdown, otherwise the current is very, very low. Here it is milliamps, here it is nanoamps. You can't compare, you can make it as zero itself in relatively. Okay, so in the whenever in the AC signal, we all know it is a first off, it's a positive cycle and the reverse cycle. So let us for our understanding, let me take that from the time t to t1 is a forward axis, that is it is a positive cycle, and from t1 to t2 it's a reverse cycle. So whenever the power is given, like in the positive cycle, the diode is forward bias and you can get an output. Okay, since it's a forward bias, you can, there is a current flow through this. Okay, and you can get the output depending upon the input, the same way the output will be. Okay, there will be a loss will be there definitely in the diode. Any equipment, there will be a power loss will be there, right? So the efficiency will be slightly reduced. Okay, you'll get a peak maximum, not at the same voltage what you get as the input. So when you get when you do in the reverse bias, then the second half of the cycle, what happens? This is a diode is reverse bias, so no current will flow through, or I can say in the nanoamps, right? So you can take as a 0 amp here. So the output will be at 0 volt. Okay, so this is the input cycle to your diode, and you can see the output only in the first half of the forward circle or positive cycle. You'll get a voltage in the same manner as in the AC signal. And in the during the second half of the reverse cycle, you won't get any voltage. Similarly, in the past half, you will get this type of rectification of the AC signal. Only half is done. So this with one diode, you can have a half wave rectifier. Okay. And if you need a full wave rectifier, you need more than one. That is 2 or 4. Here, as per the text, I just restrict with the 2 diodes, right? You can have a center tapped transformer with this. That is small difference. We have a in 3-terminal transformer, and in that you can the center will goes for the negative, miss ground. So this will split the voltage into 2. If a cycle comes here, this will invert the cycle. Not only it step down, say for example it is 240, it gives, right, for me here 15. So this terminal is plus 15, it will go from 0 to plus 15 in this cycle, means here it will go from a reverse case, 0 to minus 15. Okay, the center transformer is designed such a way that with reference to the ground, there will be an out of phase signal will be produced at the input. So first half of the cycle, if you see here at the voltage, right, it will be divided, and you can see here the first divided in two parts, plus fast. Say for example, one cycle is moving in the faster cycle, here it will move in the reverse cycle. Okay, now this is a special in center tap transformer. And the same way, right, you have here you attach two diodes here, one to the transformer one end and other end, two three terminals are there. So one terminal one diode, another terminal one diode, and another is the grounded. And when they join together, you just join and then attach a load resistor where you can take the output. Okay, here if you see here, whenever the first half of the cycle comes, the first diode, let me name as D1, it is forward bias. And here, since I told it is out of phase, when the first half of the cycle is moving here it will be negative half. Okay, so here it will be reverse bias, so no current will be flowing. So during the first half, only this diode will start to contact and the current will flow through and you get a output. During the negative half cycle of the input, right, what happens is this here it will be negative cycle will be there, but here it will be a positive cycle will be there. Like I told, it will be reversed due to this under tap. So here the current will flow through the diode and you get a output. So the second half also will get a output, but it is a positive. You will get output in a positive cycle, right? So this is the difference between a half wave and full wave rectifier. Right. So when you attach, this is the input, and if it is slightly segment your input before the diode, like A and B as in the textbook, the waveform of A is given at the point here, and at the point B, then it is the reverse one, out of phase, right? 180 degree. It's shown here. And the output will be you are getting rectified and you get the continuous half cycles. Okay, so this type we used to call full wave rectifier. Right, due to time I just simplify this fast, right? And then let us move on to another application, which is normally in our day-to-day life we are using this a diode, photodiode, in many applications, right? Even TVs and SaaS remotes, uh, more applications, whether we aware of that or not, we are using this. So normally when you have a semiconductor, I told you can excite by different process: thermal excitation, optical excitation. Let us concentrate here on optical excitation. When assigning a light on your semiconductor, whenever the energy of the light is greater than the band gap of the semiconductor, then the light will be absorbed by the semiconductor. And then what happens? The energy is absorbed, so it has to do some work. Due to this absorption, the bond will be broken and the electron will be freed in the lattice. So here in the energy structure, you can see there the valence band, a hole will be created, and the electrons means from the valence band will be excited to the conduction band. Okay, this is we is called absorption in semiconductor. So this absorption will depend upon the light energy. Okay, we all know E equal to h nu, or I can write this as hc by lambda. Okay, or I can write lambda equal to hc by E. So this E is the energy of the photon. So based on the photon energy, the wavelength, what is the cutoff wavelength, right? We can be able to calculate. If it is Eg, then this is the cutoff wavelength for this semiconductor. Okay, all right. So this, I think you can simplify this also. 1.24 divided by E in terms of EV. Okay, here you will get in lambda in nanometer, the relation between these two. So you can hear per dimension of the semiconductor. So our absorption per meter is called as absorption coefficient. Okay, here I've shown the graph of different semiconductors, and this is the wavelength. Okay, this absorption will not be same. Why, sir? Here, this even though the band is look like continuous, it's not so. Okay, there are different small difference in their energy levels. Okay, some if you go on, you can understand there are the energy states will be different. Okay, So the electron, whichever moving depends upon the energy, there has to be free states available for the electron to move, even though it is greater than the band gap. It has to go free and free states. Okay. So based on that, the amount of electron transfer will depend on. Okay. So the energy, if you increase, right, the wavelength is differ. You can see here the energy is increased in this scale. You can take the silicon, the absorption increases. Okay, but not in a same linear fashion. You can see here it's not any semiconductor, this is not linear fashion. Okay, so the absorption coefficient is not a linear. Why non-linearity is there? Because it depends on the states availability. We used to call density of states that available in the conduction band and valence band. Okay, from the number of electrons from the valence band has to move, there are electron states has to be available. It has to go and occupy. Okay, based on that, the absorption will be happening in the semiconductor. So if I take a diode and if I shine a light, the light should be greater than the band gap. And then there is something you have to technically note down. Whenever, if I have P and N, like a diode, right? The light will be absorbed throughout the diode. That means in the N side, as well as P side, as well as the depletion region. Okay, we will prefer this happens in the depletion region. Why? Because once it is happens in the N side, if suppose if I take the conduction band, let me draw quick. This is the conduction band and this is the valence band. Okay, the electron from here, it will be excited by absorbing and it will recombine with a fast. Okay, the lifetime of the carrier at this is less. It will be in nanoseconds or less than that. Okay, you can say it is in picoseconds. Okay, and the P side too. Whereas here, what happens is already we know this is a space charge region. So whenever the electrons being created, what happens? The from the P side, it will experience a electric field. It will be drifted. Okay, here there is a negative charge will be there. So once it will be drifted towards the N side. Okay, similarly the hole will be drifted in this direction. Okay, so in the photodiode, there will be a reverse bias, right? So to increase the depletion region, so that we can increase the efficiency of the absorption. Okay, the opposite senses, we have to reduce the recombination process. Clear? So we know that once the carrier has been generated, then the reverse bias, the current will be flowing up. Okay, we will get the current in the reverse bias. This current is a sensor to us. So photodiode, after absorbing, it will give the current in the reverse bias. Okay, I just skip this. And solar cell, the same thing, whatever we see in the photodiode, the same thing in the solar cell. Slight differences, we won't apply any potential. Though it is reverse bias, we'll give 0 volt. Okay, no reverse bias voltage will be given. So whatever the solar energy, right? Typically in the case of silicon, the energy will be most energy from the IR, it will be greater than the band gap, so it will be absorbed and the current will be we will get the current or voltage. Okay, so based on the intensity, we will get. So if you take IV characteristics without the light, we will get a IV characteristics like this, like we shown before. In the case of presence of light, we will used to get, even in the 0 voltage, we will get a current in the reverse current. This current normally we used to call this voltage, right? This current is short circuit current. Since it is 0 volt, we'll assume that the circuit is closed. Okay, and then we have to apply some voltage to cancel this current. Okay, so when we increase the forward bias in the solar cell or a photodiode, at particular voltage, the current will become 0. Okay, this voltage we use called open circuit voltage. Okay, so this combination, how much area this graph, right? The area it occupy in the IV characteristics will dictate the efficiency of a solar cell. Efficiency output, right? Maximum power output by the light power input what we shine on the solar cell. Okay, right. Like a quick move on to LEDs. Before going to LED, we have to understand something differ in the band structure. So far, we have seen only Y-axis with the energy. We're not worried about the X-axis. Okay, it is a two-dimensional diagram. When you include the x-axis normally we used to call energy versus k, that is momentum diagram. I'll make it very simple. The x-axis is different. Say, for example, this direction is different. Okay, say for example, here it is 0, 0, 0. This direction is 1, 0, 0. Okay, so what we can do is we can examine two semiconductors. One is silicon and gallium arsenide. And when you see the valence band maximum and conduction band minimum, they are in different direction. When they are in different direction, then they are called indirect band gap semiconductors. Okay, indirect band gap semiconductors. When the conduction band minimum and the valence band maximum are in the same direction of the momentum, then they are called direct band gap semiconductors. Why we have to distinguish? If it is direct, right, the excited electron directly recombine with the hole. Okay, otherwise what happens here, it has to move to the some other energy level. That means it has to change the direction. Okay, okay, so when the momentum is changed, the conservation of momentum will be happening during this process. So the electron has to change the direction and then it falls on the valence band. Okay, so the energy will be utilized in changing the direction rather than recombination. Okay, so direct semiconductors, direct band gap semiconductors are preferred in light emitting applications. Okay, so gallium arsenide is preferred than silicon. So our LEDs are not made with the silicon; these are made with gallium arsenide, gallium nitride. Okay, whatever in the market, they are made of compound semiconductors. So during the movement, when we have to give, not unlike in photodiode or solar cell, here it is forward bias. So whenever the energy is given to the electron will move from the n side, the band reduces and it will start to move towards the p side. During the process, in the depletion region, it starts to recombine or anywhere. Okay, during the recombination process, the excess energy will be limited as a light. Okay, so you can see here the whole electrons are recombining with the hole, and you can get the light. Okay, so the light emitted will be equal to the band gap of the semiconductor you choose. So for different semiconductor, you will have different light emission. So if I need different LEDs, okay, that means I have to change the material. Okay, here I list down a few colors, normally what we get in the market, and the corresponding materials that are used for fabricating it. Okay, right. Thank you. Questions are welcome.
Okay, students are asking about the PDF of the session that we'll share.
Sure, ma'am. Okay.
Okay, okay. And students, don't worry, we'll be uploading these videos in our YouTube channel also. So once refreshers course is completed, we will surely send you a mail regarding the files. So there is one question. Can
Yes,
you
ma'am.
please explain transistor as a switch? It's from Shivam Ganesh.
Yeah. Here I have not given the transistor actually. See, transistor basically is three terminal. You have two junction in us. In diode, we have seen only one junction. Okay, so there we have two junction joined together that forms a transistor. Okay, I have to draw a circuit. Probably, I think I will tell just simply. Okay, or I will post that in you can give a mail so that I can draw the circuit and give it to you. Okay, so you can have a two junctions there, where one we have to differentiate the regions where one is heavily doped and the region of the width, right? For example, emitter, it will be very high, base, it will be very less, and the collector region will be high. That means the width of the semiconductor will be high. These are done by some photolithography process, how it is being fabricated. Okay, so in that you have a transistor, there are different bias you can have. Okay, like we told, the forward and reverse bias. In a transistor, you can have both bias and you build up a circuit. Okay, and when you need a transistor as a switcher, you have to connect say for example, let me take a um, emitter, common emitter. I think if you are aware of this, this is the way an N type of region of the emitter is shown. Okay, and this is a collector and this is a base. Okay, this is the emitter and this is a collector. This is a bipolar transistor which I'm showing out. Okay, so when you use a switcher, normally you have to draw in such a way that whatever you give, it has to be flown up. Okay, so V in, you normally you will connect a resistance here, input resistance, and there will be output for the collector to take it out, right? And here you will draw from the bias, say, I think you hope VCC, right? And then on the emitter will be grounded. I say I put 0 volt here, right? And then say I have to connect this to this. Okay, so when you do this, what happens is this circuit will be open. Okay, it's like based on this connection, this will be equivalent to like a resistor and then kind of a switch output taking device, and it will be open. Okay, based on this, when you give a input, this will be the current flown here. I have to match the current and show to you. It can be open, that means this infinity resistance will be developing, that means no current will be flow here. It will be open, then there won't be any current output. Okay, from the emitter it has to go inside input and goes out like an output. Okay, when you based on this emitter current, right, you can have this input here, and this input is flowed to the base junction, and this will comes out a current in the output section. Okay, so whenever your emitter section is open, then it will act like a open voltage, means open switch, and whenever it is closed, we'll get a closed current. That means it's like a switch. Okay, I have to explain much better. If I want to do, I think probably I have not done here the transistor. Okay, I'll, if you want, I will give a notes to it.
Okay, sir, that is completely fine. So there are, okay. So no more questions are there in the chat box. I think time is also up. So maybe we'll end the sessions now. So thank you, students, for attending the session, and thank you, sir, for the wonderful part. So thank you so much. So we can meet tomorrow for the next day of refreshers course. So thank you all for attending.